Let's wait for 2 3 minutes. After that, I will start. Hey, good evening. So I have already in the chat box I have again given the same link so that if it stops, then the next hour you can use that link. I mean, it's not the link; the codes are given for joining. Okay, let's start. So today we will be solving some numerical problems and try to discuss the concepts of these problems and how can we interpret the results. Okay, so I have a couple of questions, like about 17, 16, 17 questions, and we will solve those and discuss the concept based on that. Okay, so this will be helpful for your exam point of view. Not exactly similar questions will come, but to some extent you can expect these kind of questions. Okay, and I can see today a subjective assignment is also there. So I think that subjective questions will also come. So practice the derivations. I'm not sure about it. So yeah, just practice the derivation. हाँ 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 हाँ, मैंने देखा है वो, इसीलिए मैं बोल रहा हूँ थोड़ा डेरिवेशंस वगैरह प्रैक्टिस कर लेना। मैं एक बार डिस्कस भी कर सकता हूँ, मेरे पास एक फोटो है इसका। So the first question was about the continuity equation. So I think both the the Euler framework and the Lagrangian framework both are being discussed. So that is done. Even in the problem solving session, I think I have done the Lagrangian method to derive the continuity equation. So just check both the methods. Next is the second one is expression of gravity. in terms of apparent gravity, radius of the Earth. So this today also I have one of the questions like this. So this is also being discussed, I think in the week 1 or week 2 somewhere. Okay, where you have to incorporate the role of the centrifugal force and the gravity. Okay, so this is the 2A. In the sample subjective assignment, 2B, it has been asked that find the horizontal displacement of an object dropped from a fixed platform at a height h at equator and neglecting the effects of the resistance and all. So what I think is that you have to incorporate the Coriolis term because from there only you can get into the displacement because there in the Coriolis term, uh, if you remember, like du dt is equal to say if you take the zonal momentum equation. So there is a term of v sin w cos phi minus v sin phi. Okay, so cos 0 is 1. So w will play a role. So when you are dropping an object vertically downwards, so that can affect the your x displacement. So just check about that. Third is explain the significance of geocentric reference frame and how it changes the equation of motion. So when we have incorporated that rotating frame of reference, remember when we have started the derivation, first the non-rotating frame, Earth is not rotating and then Earth is rotating. So when we have considered the Earth is rotating, what are the changes in the momentum equations? That is what is asked to uh, write here. Diagram. So it's small schematic diagram you can make like a body and which forces are being applied on it. You can draw those. Next is energy conservation. We have a detailed derivation. I have also done, and in the NPTEL lecture notes also it is there. There is nothing. Uh, Next is imagine a planet which is similar in size and mass of that of the Earth and rotates out engines. I think a similar question is there in the assignment also. Okay, just check with it. But it has been said that write down the curvature terms in the Coriolis force. So Coriolis force has those curvature term like we have derived the x, y, and z momentum equations, and in the spherical coordinate you have those curvature terms. Just write those things. And the fifth one is scale analysis. So these are also done, right? For example, the momentum equation for the horizontal momentum equation, you generally get a geostrophic balance. Whereas in the vertical momentum equation, you get a hydrostatic value. So a final result you know. Just you have to apply the scale analysis based on the mid-latitude based synoptic scale systems. All the values are known, right? So these are done. And the next thing, I think about the potential temperature. When adiabatically any parcel, air parcel is lifted upward, how the density changes or the pressure changes, that is asked. Okay, so all these things are being covered in the first, I think, 5 6 weeks. Just go through those because since they are giving the same sample subjective assignment, you could expect that in the exam also, in the final exam also, these kind of derivation based questions may come. So practice the derivations. I think time is there, so you can just practice it. And along with that, solve these numericals so that it is easy for solving the questions. So I have a couple of questions here, about 17, 18 questions. So we will do that. And along with that, we will try to discuss the concepts behind that. So that will be also helpful for understanding the derivation parts and all. Okay. Okay. So this is the first question which I have put. Very simple. So consider four stations. There are four stations A, B, C, and D. which are located 100 kilometers east, south, west, and north of it, station E. So let us draw a simple diagram. Okay. So you have station E, right, which is at latitude 45 degrees north. Okay. So this is being given. Now there are four stations, east, north, south, east, west. So I just put those stations. So A is here to the east, B is to the south, C is to the west, and D is to the north, right? And for each of these points is at a distance of 100 kilometers from this E point. Okay, so D is also at 100 kilometers from this E, and B is also at 100 kilometers. So all these points are at the same distance. It can be possible that it might have some different distance, but this is to simplify the thing. Okay, surface pressures are being given. Okay, at A, here the surface pressure is 1001 hectopascals. At B, it is 1002. All are in hectopascals, remember. Next, E is 1004 and D is somewhat lower than all of them, that is hectopascals, 998 hectopascals. Okay. Now, question is calculate the zonal and meridional pressure gradient acceleration. At where? So at E. At E point, what will be the uh, zonal and the meridional pressure gradient acceleration? So we know already that the suppose let us say the meridional first. Meridional means y direction. Y direction means south to north direction, right? So meridional pressure gradient acceleration at E will be what? Simple because we know this is minus 1 by rho delta P delta Y, right? This is known to us. Okay. Now, generally, the pressure of the air is taken as about 1.28 kg per meter. You can take it 1.25 to 1.28, any value. Okay. Just remember this, if it is not given in any question, whether in this exam or wherever, just remember that put it about 1.28 or 1.25 kg per meter cube. Now, if it is mentioned in the question that the air density is something, use that. Don't use this. Okay, so this is what you have. It is minus 1 upon 1.28. Now, how to calculate the delta P by delta Y? Because there are so many things and you have to calculate at this point E. So remember this, whenever we calculate the gradient, we use, suppose these are two grids. Okay, one point is here, another point is here. Use the central difference method to calculate the pressure gradient. So this is delta P delta Y, I'm sorry, delta P delta Y. So just write P of the north one, P of D minus P of B divided by 2 times the delta Y. What is delta Y? Delta Y is this. Okay, they are same, so we can write like this. Okay, use the central difference method because on each on the other sides, like E, B is in this side, B is on the other opposite side. So you have to use this kind of an expression. Okay. So generally, I don't think this kind of question will come. Just you may be asked that what is the pressure gradient force between E and D. So that you can easily calculate. Simple delta P by delta Y. Okay. But in this case, when you have 2 points in the opposite directions, you have to use the central difference method to calculate. Okay. Fine. So P of D is how much? 998. Right? So 998. Remember, these are all in hectopascals. We have to convert it in the pascals because that is the SI unit. Okay, so 998 minus B is 1002. Okay, divided by what is the delta Y? 2 times 100 kilometers. So 100 kilometers means I multiply it, so 10 cube meters, and this one has to be in the Pascal, which is 100 multiplied by 100. So 1 hectopascal results into 100 Pascal. So you can write like this. Okay, and remember this is kg per meter cube. Just remember the units that will help you to understand that what is actually happening. Okay, fine. Now, just if you can solve. So if you now solve it, then what will come? It comes out to be, let me see what is there inside the bracket. We will talk about the units later, let's say. Okay, so this is minus 400 because there is a 100 multiplied, and 998 minus 1002 is minus 400. Done. Okay, and in the denominator you have 200, and take this 10 to the 10 cube in the denominator, numerator like this. Okay, I'm not writing the units right now. Okay, so you can just chop this thing, so you get this. Okay, so let me go to the next page. Yes. So finally, you are getting your delta p delta y into minus 1 by rho, which is the meridional pressure gradient acceleration, which is about 2 divided by 1.28. And okay, let me go to the previous slide. See, there is a negative sign here, there is a negative sign inside the bracket. So it will be finally positive. Okay, into 10 to the power minus 3. And remember, this is kg per meter cube. So it will be meter cube per kg because density is at the denominator. And the bracketed term has pascals per meter. So one of the meter chops out like this, meter square. Okay, just see this. Now, Pascal can be written as Newton per meter square, force per unit area. There is a meter square here, and per kg. Meter square one. So, what is Newton per kg? The acceleration unit, meter per second square, right? So, finally, you are getting the units of the acceleration. Okay, so I am just writing the final result. I have calculated it. It's about 1.5625 into 10 raised to the power minus 3. Okay, this is not the end, Newton per kg or meter per second square, whatever you wanted to write. When we have got a value, just check the sign, which is positive. Positive means what? Northward, correct? Because this is the sign convention which we use in the atmospheric science, that positive means northward in the y direction or meridional direction. If you go to the zonal direction or x direction, you get positive means eastward, right? So this thing has to be absolutely clear. Northward means south to north, the direction of the pressure gradient. And that should be because, see, towards the north, it is having lower pressure. So pressure gradient force acts in which direction? From higher pressure towards the lower pressure. And that is what is happening. From B to D. It's going more northward. Okay, this is clear. Now let's come to the zonal pressure gradient. Okay, so it is northward, the zonal pressure gradient force. In the same way, it will be calculated. Okay, zonal pressure gradient acceleration. How we will write this? Delta P by delta. Okay, so you have again minus 1.28, and in the same way we will do. Okay, so it will be now, I think, 1001 minus 1004. These are in hectopascals. I will convert it into pascals, and this will be same. I've kept it intentionally same so that it will be easier. Okay, so this comes out to be, this is about 1.28 into 10 to the power minus. If you just solve it, all these things, see this is minus 3 into 100, so 100 will cancel, and in that way it will be, so this 100 cancels, it gives you minus 3. Minus 3 by 2 is minus 1.5. There is a minus outside, so it gives you plus. Okay. So this is simple. And this is again in Newton per kg, definitely. When you solve it, it comes out to be 1.172 into 10 raised to the power minus 3 newtons per kg. And this positive sign represents what? Eastward, right? Because this is the zonal one. So our convention wise, y direction, meridional direction, northward is positive. X direction, zonal direction, eastward is positive. And in the vertical direction, vertically upward is positive. Going towards the center of the earth is negative. Okay. So these are the couple of things. Because it's an acceleration, you should know that there must be a direction and there must be a value, magnitude. So this is how we solve this particular question. Okay. And there are many other questions in the assignments. We have discussed those earlier about the pressure gradient acceleration. So I think these part is will be clear. Okay. So if by any chance this kind of question comes, use the central difference method, numerical method to solve this particular question. Okay. So let's move to the next question. Okay. It says that for the previous question, the same way, calculate the zonal and the meridional components of the geostrophic wind. Okay, so these components have to be calculated, and finally also calculate the geostrophic wind speed and direction. Okay, so let's do that. Okay, so in the previous question, so from the previous question, let us write question. We have already found out what? We have found out that minus 1 by rho delta p delta y, that is the meridional pressure gradient force or acceleration, is plus 1.565 into 10 to the power minus 3 newtons per kg, and minus 1 by rho delta p delta x is plus 1.172 into 10 to the power minus 3 newtons per kg. This we have already found. All right, now we need to calculate the components of geostrophy. So how do we write the zonal and the meridional components of geostrophic wind? So zonal component, which is UG, is what? Is minus 1 upon rho f delta p delta y. Remember, UG zonal, but it depends on the meridional pressure gradient. Similarly, your meridional component is VG, which is positive 1 by rho f delta p delta x. All are the opposite gradients. Remember, opposite pressure gradients, but the velocity will be in the perpendicular direction. Not the velocity, scalar component. Okay, so assume, so whenever again this Coriolis parameter, if this is not given, just take it 10 to the power minus 4 per second. Okay, just remember this. Whenever if a question, if you don't get any information, just take it f is equal to 10 to the power minus 4. Okay, so that is for 45 degree. Fine. So just Do that. So now it is easy to calculate. Everything is there. So UG will be equal to minus 1 by F. Can I write it like this? 1 by rho delta P delta Y. Yes, we can write it. Make it a positive, make it a negative here. This we have already calculated. And F is known. So 1 upon 10 to the power minus 4 into 1.5625 into 10 to the power minus 3. So when you do that, it comes out to be about, this is UG, uh, okay, 10 to the power minus 3. If it comes here, it comes out to be 10 to the power minus 1. 10 to the power minus 1 in the denominator. If it goes to the numerator, it becomes 10. So how much it will come? 15.25 meter per second. Okay, this is your zonal geostrophic wind speed. Okay, now let's go to the meridional one. So what is that? VG is, remember, this is positive. 1 by F. Can I write 1 by rho delta P delta X? It can be written. Just what I will do is that I will make a negative sign. I will put a negative sign. So I'm just multiplying with minus 1 inside the bracket and outside the bracket. So this is fine. This we can do. Okay. So just now you have to just put here 10 to the power minus 4. And this is already been calculated, which is positive 1.172 into 10 to the power minus 3. In the same way, the earlier one, so it will be 10 to the power minus 1. 10 will go out up. It will be this. Okay. So this is minus 11.72 meter per second. So this negative represents what? It's the southward. And the positive in the UG component is eastward. So something like this is happening. UG is in this direction, so this is east, and VG is in south. Okay, if you have your convention like north, south, east, west. Okay, so in this way, this is how it is happening. But the net resultant geostrophic wind speed or velocity will be this Vg. And how will we calculate that? So Vg modulus, that is the magnitude of the geostrophic wind, will be simply Ug square plus Vg square. Why we are not writing any other term? Because they are perpendicular to each other, Ug and Vg. Okay, so you can just simply write this, and if you do that, that is 15 point whatever we have got, 62 whole square and this whole square, it will come out to be 19.53 meter per second. You can just do it. Okay, you have to take the square root also, so we'll get this. And how to find out the direction of Vg? Very simple. This is the vector relative thing. So you have theta, which is equal to tan inverse of the meridional component by the zonal component. Okay. So just if you just put it here, tan inverse minus 11.72 divided by 15.62. So if you do this, it comes out to be theta is equal to tan inverse of minus 0.75, which will be about minus 36.86 degrees. But from which direction? It is with respect to east. So this is the answer. Okay. So just remember this. Okay. Because tan, as you know the definition, this is your VG. Vector can be shifted. So this is your theta. Okay. So with respect to the eastward direction, it is minus 36.86 degrees. Okay. Okay. Another thing to mention, that just check whether the calculator they will provide in your exam I think in the Gmail or wherever you have your email address, it has been sent, the calculator, the sample calculator. Just check whether these things are present or not. This inverse of tan, inverse of sine, all those things. Just check it. If it is not there, then remember that the values will be given, so you don't need to worry about it. Okay, so this is the second question. So what we have seen so far, one is the pressure gradient. Yeah, yes. हाँ तो उसमें वो चीज देख लेना कि tan इनवर्स sin इनवर्स cos इनवर्स ये सब है कि नहीं. इफ इट इज नॉट देयर देन सोच के रहना कि वो लोग क्वेश्चन में दे देंगे वैल्यूज अगर चाहिए होगा. हम्म, बाकी okay, so in these two questions what we have seen, pressure gradient acceleration we have seen, which is related to the momentum equation, and the second is the geostrophic component of the winds. We have calculated the magnitude total net and the direction as well. Okay, so these two questions are now done. Okay, let's go to the third one. Yes, this is actually very important. So you will see this. So calculate the acceleration due to gravity at the equator at 45 degrees north and at the north pole. So three places we have to calculate. At the equator, at the middle, 45 degrees, and at 90 degrees, that is north pole of a planet. Now, I have hypothetically assumed a planet which has the same mass, the same radius of the Earth. That is, gravity is same, but rotating with an angular velocity two times the Earth's angular velocity. Okay, so assume that Earth gravity, which is average gravity, is 9.81 meter per second square. Okay, so why average? Because in the within over the Earth also for different regions the gravity values, actual gravity values changes. So if you just average, it will come out to be about 9.81. Okay, so now let's do this. So what are the given conditions? So the given condition is that your R is equal to RE, that is the radius of the Earth. These are the things which are given in the question. Mass of the planet is equal to the mass of the Earth. This is also given. But the angular velocity, I'm writing it omega here. This is 2 omega. Okay. Now what I need to calculate? So to calculate, so whenever solving the numericals, just write down like this, whatever is given and whatever need to be calculated. So G, the gravity, actually the effective gravity, because we can understand, you have to consider the angular velocity also. So effective gravity at 0 degree, 45 degree, and 90 degrees. All are in the north. Fine. So how to calculate the effective gravity? So for effective gravity, or sometimes it is called as the true gravity, is this. So I have a two-dimensional picture of the Earth. This is rotating with omega e. I'm writing for the Earth. Okay. So this is your RE. This is some angle phi, where phi is the latitude angle. Okay. If this is phi, then what will be this? This will be Re cos phi, because if this is phi, this will be also phi. This is Re cos phi. Perfect. Now, the next thing is what you have to. Now, since this is a rotating frame of reference, there will be a centrifugal force acting on this mass. Suppose this is a point mass. So let us consider a point mass. Okay, point mass having 1 kg. So let us say mass is equal to 1 kg of the object. Okay, so now there will be a centrifugal force which is acting from the center directing outwards, straight outwards. So this is your centrifugal force, and for acceleration. So how will you write it? It will be r omega square. So it will be Re cos phi into omega square, and this is omega e square. Okay. Now, where is the gravity? Where is the true gravity? Actual gravity. Where it will be acting? Gravity always acts towards the center. So this is the direction of the gravity. So this is your G. Okay. Now, in between, what is the angle? If this is phi, this will be what? This is 180 minus phi, right? Linear pair. Okay, so what you have therefore is this. This is your Re cos phi into omega e square, and there is a actual gravity G, and in between the angle is 180 minus phi. So the effective gravity, that is G dash, will be how much? This is our question. So G dash square will be equal to G square plus omega e square Re cos phi. So a square plus b square plus 2a into b into cos 180. Okay. So this is what you will get. Fine. So now, so G dash will be equal to, oh sorry, G dash square, let us say, G square plus, see, this term omega e to the power 4. So omega e, already omega of the earth is 7.29 into 10 to the power minus 5 radians per second. So if you take omega e to the power 4, it will be very small term. So I can neglect this. What else you have is this 2g omega e square Re, and cos 180 minus pi is minus cos pi. So it will be cos square pi with a negative sign. This is what you will get. Okay. Now, what next? So g dash square will be equal to g square. What we have got is this Re omega square cos square. All right. So now g dash will be equal to root over g square minus 2g Re omega square cos square. Fine. So g dash, can we take g common? Let us take g outside the root. So what it will be? It will be 1 minus 2g Re omega square cos square phi, and in the denominator will be g square. So g cancel. So what you get? G root over 1 minus 2Re omega square cos square phi divided by g. This will come. Now let us say that this is absolutely fine. This is okay. Now the next thing is that uh, yes. So what I will do is that now, wait a minute. Something is okay. Let's take one thing. So let's say g dash square again. If I do, so it will be g square. Okay, g square. Okay, this will be the same thing. So don't need to write all the time. So, let me see. This is, oh, you don't need to. Okay, don't need to do all these things. So just write this and try to understand the expressions. Okay, so this will be the almost the final thing. Okay, you can see it here. or keep it like this. So g dash will be equal to root over g square minus 2g re omega square cos square phi. Or the one thing you can do is that the same way which we were proceeding, in the same way you would proceed and apply the binomial expansion. That is another one you can do. Okay, so now what you have to do is that, so g dash, now in the planet space, for the planet, this is for the earth, right? For the planet, it will be g dash will be equal to root over g square minus 2g. See, for the planet, g is same, right? G is same because g is what? G m by r square, and mass and radius are the same as that of the earth. This is given in the question. Okay, so Re is also same. Only omega becomes 2 omega square. So it becomes 4 omega square. It's cos square phi. Okay, so this is what you will get. Now what you will do is that just you can have to calculate these things. So it will be g square minus 2g Re 4 omega square. So omega e square and cos square phi. So for the equator 0 degree, cos square phi will be 1. So this will be this. G dash at 45 degrees now will be g square minus 2g Re 4 omega e square into 1 by root 2 square, which is 1 by 2. And finally, g dash at 90 degrees will be nothing but g square. Why? Because cos 90 is 0. So the second term vanishes. Okay. So what you will get, g dash will be equal to nothing but g, which is 9.81. And here, what you will get, this is just one step I want to do. G Re 4 omega e square divided by 2. So I can chop this 2 out. Okay, so everywhere you can see that, particularly here, there is a larger decrement in the effective gravity near the equator. At 45, decrement is somewhat less because this 2 factor is gone from the g square, and here this is the maximum. So something like this will come if you put, now just put the values of g, which is given, Re known, and omega e. I have already written omega e. Re is radius of the earth, which is 6370 into 10 cube meters. Omega e, let me write it again, 10 to the power minus 5 radians per second. And g is given 9.81. Okay. So the plot will look like this. So for this is for 0 degrees, this is for 45 degrees, and this is for 90 degrees. Okay, and this is your g dash. So you will get something like this. This is the smallest as you go up, and finally at 9, something like this. Okay, you will get. Fine. One important thing, a question I remember from the assignment, based on the same thing, it says that at the planet's pole, what will be the gravity? So it will be same as the gravity of the Earth, whatever be the rotation speed. Because at planet's pole, that is phi is 90 degree, cos 90 is 0. So it will always be equal to the gravity. This will change only if the planet's mass and radius changes. That's all. Okay. So this is the second question. I'm not calculating everything, just keeping it like this. Okay. Fine. Let's go to the next one. Okay. This is related to the conservation of angular momentum. I think this kind of similar question is there in the assignment. So I have just taken it from there, but with a little bit of change. That is, in the assignment, it was given that the zonal speed is 0 at the equator, but I am saying that I am keeping the zonal speed at the equator as the 5 meter per second. This is the initial velocity, zonal velocity. Okay. So what it is saying is that what will be the speed of an air parcel if it starts from the equator with zonal speed of 5 meter per second and reaches at 30 degrees north. Fine. So it is just a journey from 0 degrees, which is equator, to 30 degrees north. Okay. This is the journey. And it has been said that the flow, when the air parcel starts from here, it has an initial velocity, zonal velocity of 5 meter per second. But when it goes, say suppose at 30 degrees north, so what will be its zonal velocity u dash, let's say. Okay. And this flow is being has been asked in the question that it is conserving angular momentum. Right. Conserving angular momentum. So what is the conservation of angular momentum and what is the angular momentum? How it is coming from for the earth? That is what we will try to see. Okay. So let us draw a two-dimensional earth like we have drawn in the last question. Okay, so this is your 2D earth and it is rotating with angular velocity, let's say omega. So you can see that, okay, what is your angular momentum in general definition? MVR, that is M into R cross V. And you know in the atmospheric science, we take this as 1 kg. So just leave this one. So it will be just your R cross V. And what is V? V is nothing but R cross omega or omega cross R, whatever you write. So R cross omega cross R. So this you can write. Okay. So you can see that Earth already has it as an angular velocity. So because of the planet's rotation, so L, the angular momentum of the air parcel, will depend on the angular momentum of the parcel plus the angular momentum of the planet's rotation. The planet's rotation is also there. So that will also contribute to the angular momentum. And plus, if you have a parcel which is rotating like this in the zonal direction, see, this will always come from the zonal direction, not from the meridional direction. Because you will see that your radius, there is nothing, no r vector perpendicular to the any other direction. Let's say this is your v component. Okay, you don't have any r like this. This is you generally take as the r. Okay, this will not be in a perpendicular direction. So everything will happen from the zonal direction. Okay, now let us just write it down, the angular momentum. Okay, for the parcel, it is simply, okay, this is now the radius of the earth. This is not a vector, this is only the radius of the earth. This is now the r vector, which is, if this is phi, it will be r cos phi. Okay. So can I write this as r cos phi times velocity, the zonal velocity, because from the zonal direction of the parcel, plus. This is one of the things. Second is the plan, that is r cos phi, okay, into omega cross r. So it will be omega into r cos phi, right? Because all are in the perpendicular direction. So this is perpendicular direction. So L is r cos phi into u plus r cos phi whole square into omega, right? So these are the, so total L therefore becomes r cos phi, which is taken as common, and you will have u plus omega r cos. Perfect. This is what you have got. Now you apply the, now since we have now known the angular momentum of the parcel, which is moving in the zonal direction, then applying the conservation of angular momentum, you can easily get what will happen in the 30 degrees north. And that is what we will do. So angular momentum at the equator will be equal to angular momentum at the 30 degrees north. Okay, this is what we have. So at equator, phi is what? 0 degrees, and 30 degrees north, phi is 30 degrees. Okay, so r cos 0 into u plus omega r only is equal to cos 30 is root 3 by 2, and this is omega r root 3 by 2 plus some u dash, that is zonal velocity at 30 degrees north. So finally, just do it. It's just a simple calculation. So omega r square plus u r, this is 1. Okay, and in this end it will be omega r square again, but 3 by 4 plus r root 3 by 2 into u dash. Perfect. Now this is omega r square. I will take this in this side. So it will be 1 minus 3 by 4 plus ur, which is equal to u dash r root 3 by 2. So u dash finally will be 1 by 4 omega r square coming from this plus ur divided by r root 3 by 2. So u dash will be equal to 1 upon 2 root 3 omega r, just solving all these things, plus 2u by root. Okay, so it will be just omega r plus 4u divided by 2 root 3. That is just taking the LCM, 2 root 3. This will omega r, and this will be 4u. So u dash is omega is 7.29 into 10 to the power minus 5 into r. That is the radius of the arc. This is the first term, 4 times initial velocity, 5 meter per second, and divided by 2 root 3. So if you do all these calculations, it comes out to be 139.82 meter per second. In the other case, when the initial velocity was not 5 meter per second, see, this part is 0. And we have got 120 meter per second at that time. Okay, so this is a question based on angular momentum conservation. Okay, let's go to the next question. This is a question which I have framed for a simple cyclonic circulation, and we will try to calculate the Coriolis force and the centrifugal force. Because you have seen that there are many cases like gradient wind balance or cyclostrophic wind balance where we need to calculate the Coriolis force and the centrifugal force. So this is easy question. You can see it looks a bit larger question, but it is relatively easy. So it has been asked that consider a cyclonic circulation. Okay, so cyclonic circulation means this kind of a circulation where at the center there is a low. It's a low pressure system, right? And how the cyclonic circulation looks like this and this. So winds will be moving in an anti-clockwise direction. Okay, so just time. So for the cyclonic circulation, okay, winds are anti-clockwise direction. Okay, so this has to be known. Okay, this entire thing is at 15 degrees north. So generally, a tropical cyclone or a low pressure system generally forms at the equator and it tends to move towards the north. Okay, there are reasons why it goes towards the north, but these are very complicated. We are not able to discuss that right now. But let us say that at 15 degrees north, there is a cyclone. Wind is observed, through any observation thing, maybe through satellite or through radar. We can say that we have observed the wind at 400-kilometer distance from the low pressure zone. The center low pressure zone from here at the 400-kilometer distance, both to the east and to the west side, there is an observation of the wind. Okay, so this is your east, this is your west. Okay, which is 400 kilometers from the center of the cyclone, is the wind speeds are known. And what are those? At the east, it is 20 meters per second. Here, this is 20 meters per second. And in this point, it is 18 meters per second. All right. Just the question is that calculate the centrifugal force and the Coriolis force. That's all. The simple thing is actually very simple. So let us say the east, what will be the centrifugal and the Coriolis force? So F centrifugal is nothing but V square by R. We know this, right? R is known and V is also known. That's all. So just write 20 square and R is 400 into 10 cube because it is in meters and this is in meters second whole square because it is square. So again you can see that 400 divided by 400. Can I write 10 to the power minus? Yes, you can. And this gives you the centrifugal force or acceleration is meter per second square. Perfect. So this is 10 to the power minus 3. And yeah, so this is the thing. And if you just see its direction, it will be always radially outward, that is in the eastward direction. Okay. Similarly, to the west, to the west, what is F centrifugal? We will calculate the Coriolis later. So this is again V square by R. Okay. So V is what? 20 into 20. Oh, sorry, not 20. Sorry. This is actually 80. Okay. So this is actually 18. So 18 into 18 divided by same 400 into 10 cube. And this gives you, let me check, I've calculated somewhere. Yes. It is about 9.1 into 10 to the power minus 4 meter per second square. Okay. And what is its direction? It's actually westward. Now you can ask me that why is it not coming in the sign? If it is westward, it should come at negative. This is because, see, this is your R. This is the direction of the R. So that's why it is positive. But this is the direction of the R. So actually in the R, you should have taken the negative. I have not taken because I am calculating the magnitude. Okay. Actually, it will come out to be negative. So it will be westward. Centrifugal force will be always from the center to the outward direction, radially. Okay. So this is westward. This is all about the centrifugal force. Okay. What about the Coriolis force? Okay. So for the Coriolis force, see, this is in the horizontal direction, right? So we will use the horizontal Coriolis force. That is easy. That is F K cross B with a negative sign. This is your F Coriolis, right? And what is F? Is minus 2 omega 25. Depends on the latitude K cross B. So whenever you are calculating your Coriolis force, let's say eastward, eastern side Coriolis force if you have to calculate, then just apply this 2 omega sine of 15 into V. Just write the velocity. What is the velocity at the east? Is 20. So 2 into 7.29 into 10 to the power minus 5 into sine 15. You have to just calculate this. I also don't remember the value of the sine 15. Okay, so this will be about 7.54 into 10 to the power minus 4 meter per second square. Okay, now what is its direction? How will you find out its direction? Very simple. See, here, which direction the wind is blowing? It is in the northern hemisphere. And you know that Coriolis force always turn the wind towards it to its right in the northern hemisphere. So if it is moving like this, yeah. So if it is moving like going towards the northward direction, so your Coriolis force will be eastward. Okay, so Coriolis force will be equal. Similarly, if it is moving in the southward direction, since it is in the northern hemisphere, it will turn it to westward. Okay, so you can use this also to understand, or otherwise, just write it based on your own knowledge. That is, Coriolis force acts rightward perpendicularly to the wind direction. Alright, this we can. Similarly, for the western part, you can calculate the Coriolis force. It's 2 omega and 15 into 18. So this the values are same. I'll just write down the direct value and calculate later on. 6.79 to 10 to the power 20%. Okay, and this will be what is the one thing which you know? See the magnitude. It is 7.54 into 10 to the power minus 4 in both the cases. But what about the centrifugal force? In this case, it is 10 to the power minus 3, which is quite large compared to the Coriolis force in the eastern direction. And in the west of the cyclonic circulation, it is 9.1 into 10 to the power minus 4, but here it is 6.79. So again, in both cases, centrifugal force is larger than Coriolis. But you cannot neglect Coriolis because of that. Okay, but the thing which I wanted to show is that if you don't calculate at 15 degrees and you try to calculate at 20 degrees or 25 degrees, the Coriolis force will be stronger. The more you go towards the equator, the Coriolis force becomes weaker because it depends on phi, sine of phi, and sine of 0 is 0. Okay, so more you go towards the equator, Coriolis force decreases, centrifugal force increases. So near the equator, this is one of the points. So near the equator, whenever a cyclonic circulation exists, its balance will be between the pressure gradient, which will always be there. Here also the pressure gradient will be there, but in the question it is being asked to calculate the Coriolis centrifugal. There will be, of course, a pressure gradient. So pressure gradient will be balanced by the centrifugal, and that's why we call this as cyclostrophic wind. But as you go more towards the north, the impact of Coriolis force also comes into picture. That's the main point. Okay, so this is your fifth question. Okay, the sixth one is that what will be the speed of the gravity wave? It is so simple, at a depth of 4 kilometers. So these are all imaginary fluid system, and you know that gravity wave speed which is root over g times h. So root over 9.81 into 24,000. Okay, so if you just calculate, it comes to 198.09 per second. This is the velocity. So nothing is there. The simple question. Yes. Next is, this is important, and this is there. I think this is similar kind of a concept is there in your subjective assignment questions. Also, it was there in your actual assignment. Okay, which is about the potential temperature of the parcel. Okay, let's do it. So it has been asked that what is the potential temperature of an air parcel at 850 hectopascals having a temperature of 20 degrees Celsius. Okay, so 850 hectopascals is about 1.5 kilometers. So what is the definition of potential temperature? Potential temperature is defined as temperature T into 1000 divided by P to the power R by Cp. This R by Cp value is about 0.287. Okay, so we have already calculated this. So this is known 0.287. Okay, these are for all for the dry gases. Okay, for the moist gases, it will not change much because it will consists of both dry air as well as moisture. So it will not change much. Okay, only one mixing ratio factor comes. But let us forget about that. We will use throughout this only. Okay. Now, temperature at 850 hectopascals is given is 20 degrees Celsius. Remember, all thermodynamics based questions which are there in this course always use the temperature in Kelvin, not use in degrees Celsius. Don't use it in degrees Celsius. That is 293 Kelvin. Okay. What about the pressure given? 850 hectopascal, which is fine. This is because this 1000 is also in hectopascal. Okay. So you can calculate now. So it will be 293 into 1000 divided by P. P is 850 to the power 0.287. So this goes and further calculate this will be 293 into 1.047, which is 306.9 Kelvin. Okay, that is, suppose this is your structure, which is let's say 1000 hectopascal, and let's say at a height of 1.5 kilometer, your pressure level is 350 hectopascal. Okay, here the partial temperature is 293 Kelvin. But if you take this as the reference, 1000 hectopascals as the reference, then the temperature which you will perceive of this particular parcel with respect to 1000 hectopascals is 306.9. This is the potential temperature. Potential means with respect to some reference. When you calculate in physics, let's say the potential energy, there must be a reference point. Z is equal to 0 or Z is equal to something as the reference. And then you calculate the potential energy. Similarly, this is the potential temperature. Okay. So what is the importance of potential temperature? The importance of potential temperature is that this remains constant for dry adiabatic fluid. That is for the parcel motion. Okay. We will have a question where we will apply this conservation. Okay. And next is that if the lab state of the parcel is given like these two conditions, then what can you comment about the atmospheric stability? So you know that your stability can be found out like this. T by theta d theta dz is equal to gamma of parcel minus gamma of environment. Okay. So if gamma of parcel is greater than gamma of environment, d theta dz becomes equal to or greater than equal to 0, greater than 0, sorry, this becomes a stable condition. Similarly, if d theta dz is less than 0, it's unstable. Okay. And if it is equal to 0, it's a neutral condition. So it's fine. So We will just calculate this, right? Because parcels lapse rate is given, and I know that environment's lapse rate, that is gamma of E, average environment lapse rate is 6.5 degrees Celsius per kilometer. So very clearly in the part A, where the parcels lapse rate is 5 degrees Celsius per kilometer, is less than 6.5. So gamma P is less than gamma E. So in part A, that is gamma of P is 5 degrees Celsius per kilometer, is of course less than the gamma E. That means your d theta dz should be less than 0, which is unstable condition. But how will you understand it? So for that, make a simple diagram. See, this is your environmental lapse rate. Let's say that is gamma E. But what about your gamma P? That is 5 degrees Celsius per kilometer. The decrease is your much larger, right? 5 degrees Celsius per kilometer, like this. So this is your gamma P. So at any height, look at the temperature of the parcel. It is here. Look at the temperature of the environment. So you can clearly see the temperature of the parcel is greater than the temperature of the environment. If parcel's temperature is greater than the temperature of the environment, the rho of the parcel, density of the parcel will be less than the rho of the environment. Yes. So if it is true, density of the parcel is lower than that of the environment, then it is buoyant. The parcel is buoyant, so it will immediately move upward. Okay, and that is the condition of unstable atmosphere. Next is B, where gamma P is, I think, 8, right? What's that? 8. So 8 degrees Celsius per kilometer. That means, see, this is gamma P. 8 degrees Celsius per kilometer means what? It is decreasing at the rate of 8 degrees Celsius per kilometer, which is greater than gamma E. So if the lapse rate is greater than your gamma E, so this is the environmental lapse rate, gamma E again. But for the parcel, it is like this. More decrement. Okay. So this is the gamma P. So again, at any height, this is your temperature of the parcel. This is your temperature of the environment. So clearly, Tp is now less than T, or rho P will be greater than rho. If this is the condition, then it is more weighted, so it will be falling downwards. So it says stable atmosphere. Okay, so this is what your atmospheric stability part. Okay, fine. Next is uh, calculate the density of the air parcel that is lifted dry adiabatically to 500 hectopascal, having a temperature of 20 degrees Celsius at 850 hectopascal. Okay, this is not a very tough question. Simple thing is that what is given? Given that your T1, that is initially, it was at 850 hectopascals and its temperature is 20 degrees Celsius. So again, I have to convert it into Kelvin. P1, initial pressure, my parcel is at initial pressure of 850 hectopascals. Let's keep it like this. Okay. But now it is being lifted dry adiabatically. Very important, dry adiabatically to another level, which is P2, which is 500 hectopascals. Calculate your density, rho 2. Okay, this is what it is here. For density, what do you require? Yeah, T2, the temperature. Understood? This is what the question is. Thing is that when you will be asked that it is dry adiabatically lifted, just use, so we will be using the potential temperature conservation. because this is the only thing which is conserved in the what you call as your dry adiabatic process. So what is theta? Let's say at 1, at 850 hectopascals, it will be T1 1000 hectopascal divided by P1 to the power R by CP. R by CP is now 0.287, so we can easily write it. This we have, I think, already calculated, which is 306.9 Kelvin. Right? This is your theta 1. And conservation means what? Theta 1 should be equal to theta 2. So now theta 1 is known. What is theta 2? T2 1000 divided by 500 to the power 0.287. Perfect. So this becomes 2. T2, can it be written as P2 divided by rho 2 times R? Yes, 2 to the power 0.287. I need this rho 2. All right. So, oh, yeah, I think I have to add a slide here. Okay. So now, now theta 1 is equal to theta 2, which is equal to P2 divided by RD. RD is what? 287 for the dry gas. So R is equal to RD, the dry process, which is 287 joules per Kelvin per kg. Okay, and rho 2 is there, which is 2 to the power 0.287. Theta 1 is known. P2, now this has to be written in Pascal. So P2 is what? 500 into 00 in Pascals. 287 divided by rho 2 and into 2 to the power 0.287. So rho 2 will be equal to 500 divided by 287 divided by 306.9 into 2 to the power 0.237. This should be the answer for the rho 2. And if you calculate it, comes out to be 0.692 kg per meter cube. Okay. So as you can see that density also decreases with height. This should be the okay. In I think it's a similar question, but in that case it was in 0.725 or something which we have got. Okay, so this is one of the questions for the dry adiabatic process or the parcel conserving the potential temperature. Fine, it's done. Next, an air parcel has a potential temperature of 300 Kelvin at 1000 hectopascal. The change in potential temperature with height is this. What is Brandt-Weissala frequency? This is easy question because everything is given. There are more tough questions in the assignments. So theta is given to be 300 Kelvin. Pressure is 1000 hectopascals. Okay, just tell me one thing. If the potential temperature is 300 Kelvin at 1000 hectopascals, then what will be its temperature at 1000 hectopascals? It will be the same, right? Because theta we have defined as what? P into 1000 divided by P to the power R by C. So P is 1000 in our case. So theta is equal to. Okay, fine. This is the thing. Also, d theta dz is given, which is 0.005 Kelvin per meter. And what is your Brandt-Weissala frequency? This square of Brandt-Weissala frequency. So if n is Brandt-Weissala frequency, then n square is defined as like this. We have derived this. So check all those derivations. Okay, be careful. Check all those derivations because it is now the subjective questions may also come because today I have seen that into 0.005. So n square will be about, right? So n will be square root of this, which is equal to 0.012, and it is depending how or per second dependent. All right. So this is another question. Okay, let's move to question number 10. This is the 10th question. This is, I think, from the assignment only. Just give me a moment. Okay. So suppose a 1 kg of parcel of dry air is rising at constant vertical velocity. If the parcel is being heated by the radiation, what must be the speed of the rise to maintain a parcel at constant temperature? Simple thing is that you need a radiation rate of this. Only one equation throughout the whatever equations we have studied is the thermodynamic energy equation, in which you can incorporate this term, thermodynamic energy equation. Okay, so what was that? dq dt is equal to cp dt minus alpha dp dt. Alpha is what? Specific volume of the gas. Okay, this dq dt is given. Fine. Okay, this is given. What else we can write? So this is now cp dt by dt minus alpha. Now dp dt can be written as dp dz into dz dt. Okay, and dp dz from the hydrostatic approximation is minus rho g. This is what? W. So cp dt by dt minus becomes plus alpha rho g w. Now alpha is v by m, rho is m by v. So rho into alpha will be what? 1. So this goes. This will be equal to your dp dt. Fine. Now for the cp, can I write these terms as like this? Local derivative plus the horizontal advection plus the vertical advection plus GW is equal to dq dt. What next I will do is that I will divide by Cp. So delta T. So these things are not given. So put this equal to 0. Whatever is given, I will take that. Plus GW by Cp is equal to 1 by Cp dq dt. We can write this. Now what is G by Cp? Is gamma D. Remember, dry adiabatic lactate is G by Cp. Okay, so this is now done. So finally, again I have to take a slide. Okay, so this is done. So finally we can write W, take common. This is delta T delta Z, which is normal lapse rate gamma D is equal to, this is 3 into 10 to the power minus 1 divided by the Cp. Cp is 1005 because it's a dry. Cpd is 1005 joules per Kelvin per kg. Gamma D is generally taken as 9.8 Kelvin per kilometer. and gamma is 6.5 Kelvin per kilometer. Okay, this is environment lapse rate. This is dry adiabatic lapse. Fine. So this is gamma T minus gamma. Why? This is actually minus delta T delta T. Minus. So that's why. Alright, so everything is there. Now you have to just calculate. So W will be equal to 3 into 10 to the power minus 1 divided by 1005. 9.8 minus 6.5 is about 3.3. But remember, this is Kelvin per kilometer. So can be written as 1000 meters. So 3 into 10 to the power minus 1 into 10 cube divided by 1005. Okay, if you solve everything, it will come out to be about zero point 0.09 meter per second. So roughly around 1 centimeter per second. Okay. So this question is already been given, so I'm not giving much time to it. Further, this is also given, but I have changed something values maybe. Geostrophic wind when there is a height increase of 20 meter per 100 kilometer. So when you have this, means it is the pressure coordinate. We generally use the Cartesian coordinate x, y, z, t, but this is for the pressure coordinate. And what is the velocity for the pressure coordinate? Is simply Vg is equal to only one component I am writing, delta phi delta x. Can be written as 1 by f into g delta z delta. Okay, where phi is geopotential, just quickly writing it, which is equal to g times z. This is the geopotential height. So it has been asked in the question, when this geopotential height is changing at a distance of east, then what will be the geostrophic wind? So when it is changing with respect to east, that is zonal gradient is there, you only get the meridional component of the geostrophic wind. So simply Vg, this is known. You can take 10 also, 10 to the power minus 4. If so, if it is given here, so it's fine. And what is delta Z delta? It is an increase, so plus 20 divided by 100 because I have to keep it in meters, SI unit. So it will come out to be around 20 meters per second if you just take this value as 10. So this is about 20. Okay, this is the question. Now, okay, this is now the scale height related question. We have done some questions based on that. So again, I will do one. Okay, so this is for the oxygen atom. So what is the molar mass for the oxygen atom? O atom. It's only atoms, remember, so it is 16 grams per mole, right? Yes, because O2 is 32. Temperature is given. So what is your formula for scale height? This R star T divided by mg. R star is universal gravitational constant. Okay, which is equal to 8.314 joules per Kelvin per mole. T is temperature, M is molar mass. So you can use any other expression based on Boltzmann constant also, but I find this expression to be much more useful. So R star is 8.314, T is 300 Kelvin, mass is 16 grams per mole, and G is 9.81 meter per second square. Kelvin into joules per Kelvin mole. This is the unit of this. Okay. So this mole and this mole goes, Kelvin and this Kelvin goes. Okay. One thing is that this is in grams. I have to convert it into kg. 8.314 into 300 divided by 16 into kg will be 10 to the power. So you have to multiply by this. So this will be kg. Okay, no, this is gram. This becomes kg into 9.81 meters per second square. So now only thing which you have to do is calculate. Okay, this is gone now. This is my kg. So yeah, if you have all these calculations, if you do, it comes out to 15,890 meters, which is roughly around 16 kilometers. So if you have oxygen atom in an atmospheric column, the pressure at the surface will decrease to the rate of 1 by E. So 1 by E times P naught will happen at 16 kilometers if the temperature of the column is constant. Okay, right now I will skip this question because it's a long question. If we have time later, we will see, because this is a bit difficult. So we will do it later. Let's come here because these questions may come, which is based on the. Okay, this is also related to the previous one. Let's leave this one. Let's come to this. Okay, there are two questions, this one and the next one, and then we will see whether we will have time. Then we can do it. But this is important. So a ship is swimming northward. Okay, a ship is swimming northward. So suppose this is the northward direction at 10 kilometer per hour. The surface pressure increases towards the northwest. So if this is north, what is the northwest? This is the northwest. Okay. So 45 degree from the north, 45 degree from the west. Okay. Pressure increases towards northwest. So in this direction it is increasing at rate of 5 pascals per kilometer. What is the pressure tendency recorded at a nearby island? If the pressure aboard the ship decreases this. So it is given. Remember, whenever a station is given, there the local tendency or local pressure tendency is being calculated. So given dp/dt is this. What is the ship is measuring? So it is decreasing 100 pascals per 3 hours. Okay. Now it has been also given that your pressure is increasing at 5 pascals per kilometer in the northwest direction. Remember. So delta P delta X, which is in this direction, this will be positive because it is increasing here as well as here. So it is 5 pascals per kilometer into cosine 1 by root 2. Similarly, delta P by delta Y is 5 pascals per kilometer into 1 by root 2. Cos phi sin phi, simple. If this is increasing here, there is a component here, there is a component. Simple. All right. But the the ship is streaming northward. So V will come, U is 0 at 10 kilometer per hour. So mostly everything is there. I need to calculate. So to calculate the delta P, the tendency, local tendency. This is I need to calculate. So how we can write? I know that dp/dt is equal to the local delta P delta T plus U delta P delta X plus V delta P delta Y, and there is also W delta P delta Z. But is any information about W or delta P delta Z given? No. So keep this 0. U is 0. So this term goes. Only these two terms remains. So delta P delta T is what I need to calculate. dp/dt is given minus V delta P delta Y. So V is also given. delta P delta Y also we have. So just we need to calculate. So delta P delta T will be equal to dp dt is minus 100 pascals by 3 hours minus V is not for so 10, which is plus. Okay, and remember this is in kilometer per hour. Just be careful. Into increase of pressure, that is 5 pascals divided by root 2 kilometers. See, this kilometer and this kilometer goes. Okay, so what we get? Minus 100 by 3 pascals per hours minus 10 into 5, 50 by root 2 pascals per hour. So which comes out to be around, I think, minus 68.7 pascals per hour. Okay, this is the answer. Fine. So this is your local at a particular island, at a particular station. How much is the change in the pressure? Okay, so this is your question based on the local derivative and the total derivative. A similar question is there. Let's do that. Fine. Temperature at a point 50 kilometer north of the station is 3 degrees Celsius. So let us. So this is suppose a station. Okay, this is suppose a station, and let us say that the temperature is T at the station. Now, northward at 50 kilometers. Okay, temperature is T minus 3. Okay, if the wind is blowing from the northeast, so this is your north. So northeast will be blowing from the northeast. So like this. Okay, northeast at 20 meter per second. Also, the air is being heated at a rate of 1 degree Celsius per hour. What is the local temperature change at the station? So, given conditions, let us write quickly. dt by dt heating rate is given, which is 1 degree Celsius per hour. Okay. Delta T by delta T, I need to find out. Okay. Now, wind. Okay. So, wind is from the northeast direction, right? So, this is how it will be. So, this is the west direction and this is the south direction. Because it is coming from northeast, so this will be 45, this will be 45. Okay, and what is the resultant is 20 meters per second. So you know that u will be what? 20 by root 2 with a negative sign, and v will be what? Okay, minus 20 by root 2 meter per second. 20 cos 45, 20 sin 45. Simple. And negative for the directions west and south. Then what else? Have they told you about how the temperature is changing in the east-west direction? No. Have they told you about delta T delta Y? How it is changing in the meridian direction? Yes. 3 degrees Celsius decreasing at 50 kilometers. So that's all. Everything is now given from the question. You just have to apply. So what we have written earlier, delta T, the local change which we need to calculate, dt by dt minus u delta T delta x minus v delta T delta y. I am not writing the w term because it is not there. Delta T delta x is 0, one term is gone. This is known, minus v is minus 20 by root 2. Okay, this is meter per second, and delta T delta y is minus 3 degrees Celsius per 50,000 meters. Okay, everything if you do it will be 1 degree Celsius per hour. This becomes plus and there is a minus. So this comes out to be 0.000848 divided by 3600 seconds to degree Celsius into 360. This 3600 seconds is hour. Okay, and everything if you do I have here. So delta T is 1 degree Celsius per hour minus this will come out to 3.05 degrees Celsius per hour. So comes out to be minus 2.05 degrees Celsius per hour. So what do you see? That the local temperature, the temperature decreases at the station when you have such kind of an atmospheric conditions nearby. Okay, so this is done. So this is about the advection and the local tendency terms. And there is a very good question in the one of the assignments which we have solved. Just check that also. This is related to the ionosphere. So it has been asked that if the recombination rate of a reaction is 10 to the power minus 8 centimeter cube per second, then calculate the value of the time constant. Okay, so it is given that the recombination rate alpha is 10 to the power minus 8 centimeter cube per second. Can we write it in meter cube? So 1 centimeter is 10 to the power minus 2 meter cube. Sorry, meter. 1 centimeter cube is 10 to the power minus 6 meter cube. So just alpha can be written as 10 to the power minus 14 meter cube per second. Also, the electron density is 10 to the power 12 per meter cube. Oh, now what is the time constant? Time constant tau is Ne into alpha inverse. So Ne is 10 to the power 12, alpha is 10 to the power minus 14 inverse, which will come out to be 10 to the power minus 2 inverse, which is 10 square, which is 107. Okay, so this is how we calculate the time constant. Fine. Let's go to the, I think this is the last one. But before that, I will try to see that whether I can do that particular question or not. But this is simple. If the electron density of an ionospheric layer is given to be this 8.1 into 10 to the power 11 per meter cube, then maximum frequency of the radio wave that can be reflected back. So this frequency is given as by this 9 root n e. So F comes out to be 9 into 8.1 into 10 to the power 11. So F, see, this 9 can be taken inside. Right? So 81 into 8.1 into the power 11. So root over 81. Can I write this as 81 into 10 to the power 12? So this square root will give you 181 and this is 10 to the power 6. Right? Oh, answer. This will be 10 to the power 10. 5. So it will be 8.1 into 10 to the power 6 hertz. So it will be 8.1 megahertz. This frequency will be reflected back. So these are the two questions related to the ionosphere part, which I thought to discuss. And now I can go here, but this will be a bit lengthy. But let us do this. This might not come, but at least a concept should be clear. Okay, this is related to the thermal wind. So the mean temperature in the layer between 750 hectopascals and 500 hectopascals. So this is 750 and this is 500. Okay, The mean temperature here, that is T bar, it decreases eastward by 3 degrees Celsius. So delta T by delta X is minus 3 degrees Celsius per 100 kilometers. If at 750 hectopascals, geostrophic wind is from the southeast, means this way. So this is your east and this is your south. Southeast direction at 20 meters per second. What is the geostrophic wind here? So what is Vg at 500? You know that thermal wind Vt is nothing but Vg at upper 500 hectopascals minus Vg. This is another definition of the thermal wind, 750 hectopascals. Okay, Vg at higher pressure level minus lower. That's why it is defined as the vertical shear of geostrophic wind. So at different levels, what is the difference between the geostrophic wind? Also, this Vt can be written as R by F A cross grad T log of P naught by P1. This we have already discussed. Okay, so the meridional component will be R by F delta T delta X log of 750 divided by 500 because the lower pressure is 750. So once you do that, your Vt will come out to be minus 34.91 meter per second. So okay, R is 287, F is 10 to the power minus 4, delta T delta X already given, and log value you can use. Fine, so this will come out. But what about UT? Nothing is given because delta T delta 1 is 0. Nothing is given here. So UT, the zonal thermal wind is 0, but VT is there. Okay, now let us consider now the 750 hectopascal. What is being given? That your geostrophic wind UG, this is your east, this is your south, this is the direction of the geostrophic wind. So this is 45, this is also 45. So UG and VG you can get. This is your UG and this is your VG. UG is what? Minus 20 by root 2 meter per second, which is minus 14.14 meter per second. And what about VG? Plus, see, northward. So 20 by root 2 meter per second. This is plus 14.0. Okay. Therefore, now the VG at 500 hectopascals will be equal to VG at 750 hectopascal plus V thermal as per this definition. This. So this will be what? Plus 14.14 and Vt is minus 34.91, which comes out to be minus 20.77 meter per second. Negative represent downward because we are talking about Vg. But what about Ug at 500 hectopascal? Is Ug at 750 hectopascal plus Ut. So this is minus 14.14 because this is 0 meter per second. Again, negative mean it is westward. Okay. So finally, if you have to calculate Vg net, simple it is at 500 hectopascals is just Ug square plus Vg at 500. So this gives you about 25.12 meters per second. This is the magnitude. But what about the direction? Direction will be tan inverse of your Vg divided by U. Okay, so if you do that, it will come out to be about 55.75 degree with respect to west. Because both are negative, correct? Both are negative. So Ug is here, westward, and this is southward. So this should be the, what you call as your, so theta is like, okay. So this is what you will get. Fine. So this is the question which I wanted to ask. So it consists of two things. One is the this definition of the thermal wind, which is the shear of geostrophic wind. That is geostrophic wind at higher pressure, sorry, the higher altitude, lower pressure minus geostrophic wind at lower altitude, higher pressure. And this is the definition of the heat. So based on that, it's a bit tough. If you want, you can just practice it. If you don't want, leave it. I don't think this will come. And finally is this mean temperature advection. So already you know that delta T bar by delta X in the previous question is minus 3 degrees Celsius per 50 kilometers on 100 kilometers. So this is already been given. U bar will be what? Simple. U at 500 plus, because mean advection is there. No? So you have to do this by 2. Just average it. So U at 500 was, I think, just 14.14 with a negative sign. Okay. And at, so what is U bar at 750? Okay, so this is minus 1, 14.1. Oh, this is also minus 1. All are minus 14.1. So divided by 2 will be also minus 14.14 meters per second. So that's all. Everything is done. So zonal advection will be minus. So remember, this is the advection. Always remember it is negative. U bar delta T bar by delta. So this becomes 14.14 into minus 3 degrees Celsius divided by 100 into 10. So it comes up to minus 4.24 10 to the power minus 4 Kelvin per second. Because this is the change. Remember, change can be written to change in temperature can be in both degrees Celsius or Kelvin. But actual temperature, like for the potential temperature calculations, you have to write it in Kelvin. Okay, so this is the final result. I think these are all the questions which I have now. Yeah, if you have any other queries, you can ask. So we have solved lot many numericals today and discussed the concepts. Okay, I will share it with everything. So this is the last session. So couple of things that practice these questions or the assignment questions as well, the numericals, subjective assignment, whatever is given. So based on that, try to practice the derivations of important formula, understand the terms properly, and yeah, practice through the calculator. Use the numericals and the calculator which is given. Just practice it so that at the time of the exam you can easily do that. Okay. And what else? Yeah, revise all those concepts. We have time, and that's all. All the best. Now, if you have any questions, then okay. हाँ हार्ड तो है एडवांस लिखा हुआ है ना तो हार्ड तो हो गए हाँ हम्म बहुत कुछ एक साथ है एक्चुअली। हम्म। बहुत कुछ है। हम्म। ये तो है। नहीं, बट प्रैक्टिस करना पड़ेगा, डेरिवेशंस वगैरह प्रैक्टिस करोगे तो हो जाएगा।